All right, so now that we've taken it up a step and talked about lists, we're ready to take it up yet another step and talk about data frames. So remember in SAS, we went straight to data sets, but we have a lot more complicated data structures in a programming language like R. So we're just now getting to the idea of a data frame, and it's basically a data set. It has a matrix-like structure where the columns are your variables, the rows are your observations. Each column is an element from a list, and each element has the same length as well. So a data frame is going to be our most fundamental structure that we use when we call statistical functions. So if you want to build, say, a linear model, you're going to need to have your data in a data frame. Each column, like I said, may be of a different type. So if you pull off, say, the variable population here in this picture data frame, that would be a column vector for population or a column vector for income. So what's interesting about R is it's almost like composition objects. And so we have an object here that's a data frame, but it's composed of many different objects that have different compositions. And we could actually pull off, using indexing, pull off different elements, different columns, different rows, however we want. We're going to be talking a lot more about managing these kinds of structures in R in a later lecture, but for now we're going to just think of it that way, as a combination of these more fundamental object types in R. So we're going to go on and talk more about the elements themselves. So when we have data that's stored, whether it be in a vector, a matrix, an array, a list, or a data frame, it could be numeric, it could be logical, it could be character, it could be a factor, or it could be a date value. And we're going to talk about all those types here. So numeric data is going to generally pretty much always be double, even if we are thinking of it as a count variable, which would technically be an integer, unless we declare it as an integer valued variable, it will regard it as a double, which usually does not hurt. We can talk about that a little bit more in detail, but it's not really all that important. You can run the machine, .machine, and it's going to give you the numeric characteristics of your current installation and how it's running in R. And it's also going to give you that largest integer of the machine's precision, so you can check that out on your own, just so you know, especially if you're running R on your own laptop. Finally, format is going to provide information about the format of the object, or going to change the formatting of the object. I often use format to make things print the way we want it to print. So for example, we might want to include 3 decimals after 3 places past the decimal. So sometimes when you're presenting a table of p-values, you want everything to have the same alignment and have the same number of digits to the right of your decimal. And so using n small equal 3 with the format statement would ensure that everything, even if it cuts off after the first decimal place, that it will include tailing zeros. You can include scientific notation. You can trim the numbers. You can not trim the numbers, and so on. This is another useful page to print out and keep for your own reference. These are all logical values, so if x and y are logical valued, have logical valued elements, we can use all of these kinds of expressions. Study this on your own. This is going to come in handy on your first homework. Finally, making use of a few of those logical operators, let's create something like a numeric vector. So we just have the sequence 1 to 10, and here we do division, modular division of our vector x, and look at which elements are greater than 5. Okay, so let's think. When we divide 1 by 2, do we get 0 or a remainder 2 or of 0? Notice we would not when we have 1. So this is a false on this side. Also 1 is not greater than 5, so we get a false. But once x becomes 2, 2 divided into 2 gives you a remainder of 0. So this evaluates as true. This evaluates as false, of course, but it's one or the other because this vertical line stands for the logical operator or, so we get a true there. Notice we'll get a false for the first here, but we'll also get a false here, so we get a false for the logical operator or. Finally, we get a true here because, again, this one will be true. Once we get where x is above 5, starting here in the 6th element, we just get trues across the board. Okay? We can pull off what those are by surrounding this whole expression in brackets and with a leading x in front. And so that'll pull off those elements 2, 4, 6, 7, 8, 9, 10, where one or the other of those logical tests were true. We can do other types of operations. This might help you on your homework, so take a look at all of this. Make sure you understand it. The all function and any function are very useful. So any says, are any of the elements greater than 5? Well, that would be true because the elements 6, 7, 8, 9, and 10 are. But we could also ask the question, are all of the elements greater than 5? In that case, no. So we get a false. Little bit more about testing equality. Let's say we have a name and we want to test it for equality to this character string, which happens to be the same here. If we want to test, we need to use a double equal sign, or we can use an exclamation equal sign, which stands for not equal. You can only do it this way if you are absolutely sure that nothing could go amiss using that method. Otherwise, identical might be a better one to use overall. In general, the logical operators don't always produce something as a single value and may even return a missing or not available or a not a number result. So that's not available, and that NaN is not a number in R. So sometimes it's better to use the function identical, which took me a while actually as a programmer to catch on to. I used to always use these logical operators, not realizing that at times it's better to use identical because it does return that single logical value at the end, whereas the other logical operators do not always. Okay, so for an example, here everything's good. Okay, but up here, down here, if we have name equal to not available and we do the test, if name equal Nick, we're not going to get a true or a false. It's going to in fact tell us that there's an error in that programming expression. However, if we said use the function identical name comma Nick, we do get what we really want as the right answer of false. So just a little hint there. A little bit more about this. All equal objects are going to be treated as equal if the difference is probably the result of only inexactness due to floating point calculations. So this would be very trivial errors just due to rounding in the machine. This often will not happen if you just increase the capacity for the number of digits included in calculations in your programming environment. But even then, sometimes you can get those inaccuracies included. And so those all equal objects is going to ignore that little bit of imprecision in numerical calculations. So it's going to return a true if the mean relative difference is less than some specified level of tolerance that you would regard as reasonable. Okay. Do note that all equal will return a character string that describes the difference if it's not identical or not equal. And so there may be times that you actually want to use identical instead. So for example, here it's saying is x squared equal to 1, and it doesn't give you a false, but it instead says the mean relative difference is 0.5. Well, that may not be what you want. So maybe running it through identical or is true would be better. And then it'll give you back that what you really want, which is a false. Again, here's some functions you can use on character strings. Another good one to print out and keep. This is for your reference. A lot of these are really going to be useful, especially as we start working on how we create our reports and making them look nice in R. Here's just some examples. I'm not going to go into a lot of detail. Just make sure that you can go through and you understand what's happening here. In general, you know, we have functions that just evaluate character strings, but this cat function I use all the time, and what it really does is it joins together different character strings, and you can define how they get separated or how they get combined, I should say. Similarly, the paste function I also use a lot. It can create character strings that are a combination of two other separated character strings. You can actually specify your separator too, which is really nice. The opposite of those, though, is you can split strings. Okay, so if you have, say, a long genetic sequence and you want to split it into units of size 2, you can do that across the entire split sequence using the string split function pretty easily. You can print out from a first to last and iterate through all of the possible combinations, or you can just print out a certain number of characters. So this would print out the first 3, for example. You can also convert to uppercase, lowercase, all those things that are on this previous slide. Finally, pattern matching is often really interesting and useful when you're trying to automate processes in R or write an algorithm to automate a process. I use this a lot when I'm wanting to evaluate more complicated models and I want it to be automated in R. So a regular expression is going to be a pattern that describes a set of strings. We have a number of kind of notations to help us understand this. Is useful with a whole class of functions that you can find out more about by running the help file on regexp. And here's just an example of a little bit of what you can do with this. This, again, is useful when you're analyzing long character strings. I put this in here because I do have a lot of people from statistical genetics that take this class, and this is a really essential tool. So, for example, I'll just go over this first line. Running the function grep with red in quotation and on the colors function call will tell you all the colors that you could get from this colors function that contain red. If you put in just the caret top here in front of the red, it's going to just give you colors that start with red, or the $sign here at the end would be the ones that end in red, and so forth. So there's all kinds of ways that you can search objects or functions within R, or I should say the output from functions within R, to obtain or select certain types of results. Again, very useful when you're trying to look for, say, islands within a genetic sequence or something like that. Let's stop here and we'll finish up in the next